Here we have lesson 82. In this lesson, we will address the application of differential equations, and the types of differential equations that we'll be looking at will focus on variables separable differential equations. Here is example 1. Newton's law of cooling states that the rate of change of temperature dt by dt of an object is proportional to the difference between its own temperature T and the ambient temperature, so the surroundings temperature, TA. Ms. Kuhn poured a cup of coffee with a temperature of 80 degrees in a room where the temperature is 20 degrees Celsius at 7:30 a.m. The coffee cools to 70 degrees Celsius at 7:45 a.m. Part A. Find the temperature of the coffee at 9 a.m. So we're going to estimate the temperature of this coffee at 9 a.m. by using a function of temperature with respect to time, so T of T. Since we know the relationship between the rate of change and the gradient, the temperature gradient between the temperature and its surroundings, we can first set up our basic differential equation. And I'm going to say let T be the number of hours after 7:30 a.m. Okay, so T equals to 0 is 7:30 in the morning. And here we are given dt by dt. This rate of change is proportional. So from yesterday's lesson, we know that proportionality constant K can be introduced to the difference. So now we have to find the difference between the surrounding temperature and the actual temperature of the coffee. Sometimes it's convenient to say that because we know that this is a decreasing rate, we could put a negative sign here. But if you don't put a negative sign here in your original question, K should still work out to be a negative value instead of a positive value, okay, when you do the work. So either way, it's fine. So now let's try to separate the variables. I have big dt over t minus 20 on the left side, and I'm going to put the little t time on the right, and we know the next step involves taking the integral of this statement here. Left side becomes ln of t minus 20, and it's still that. And then on the right side we have negative kt plus c, which means that t minus 20 can be written as e to the power of negative kt plus c. And yesterday we said that e to the power of c here can be written as a. And I have a e to the power of negative kt little t plus 20 equals to the temperature of the coffee. So here we are working our way towards the function of temperature versus time. Then, in order to find A and K, my constants, I can make use of some of the initial conditions or conditions given in the question. So here we're told that we started at a temperature of 80 degrees Celsius in the room, in this part here, at 7:30. And then the coffee cools to 70 degrees Celsius at 7:45 a.m., meaning that I actually have two data points to work with. I will start with the first one, 0 and 80. I have 80 equals to a times e to the power of 0 plus 20, meaning that a is equal to 60. And then in here, I can improve my function t as 60 e to the power of negative kt plus 20. Then I can make use of the next data point at 7:45, which is 15 minutes after, but we're doing it in hours, right? So 15 minutes is a quarter hour, and 70. And I have 70 equals to 60 e negative k multiplied by 0.25 plus 20. I have 70 minus 20, which is 50 over 60. So this is 5 over 6. If I ln both sides, this way I'm going to have negative k over 4, meaning that k is equal to negative 4 ln 5 over 6. Okay? So now we have found the values of both k and a. Let's swing it to the side here. And write out our function t, which is equal to 60 e negative 4, well, negative k, so 4 ln 5 over 6 t, let's put t here, plus 20. And we can answer the question at 9 a.m. Okay, time. We are an hour and a half after 7:30, so time is 1.5. And so we have got t equals to 60 e to the power of 4 times 1.5, which is 6, ln 5 over 6 plus 20. Using my calculator, this temperature is roughly equal to 40.1 degrees Celsius. 3 significant figures. So we say that the coffee is 40.1 degrees Celsius at 9 a.m. Okay? Part B asks for the time at which the coffee cools most quickly. So we can take a quick look at the differential equation that we have. The differential equation itself, dt, well, we know what k is, but I don't really care. This is our differential equation. Let's analyze this. Negative k, this is constant, right? So it doesn't really affect, the change, because no matter what, change we have, we still multiply by the same number. But this rate of change, dt by dt, is proportional to the difference between the temperature of the coffee and its surroundings. So what will guarantee that we have a largest value generated from the right side of this equation? Well, the largest value will come from having the largest difference in temperature, right? Say in the beginning you have like 80 minus 20 at time t0. And then at 7:45, we said that this is 70 minus 20. So notice how the value of dt by dt is the greatest when I have the largest difference in temperature, okay? Therefore, the coffee cools most quickly, okay, in the beginning. 30 a.m. Okay. Okay, here is example 2. Water flows out of a tap at the bottom of a cylindrical tank with base radius 1 meters. The rate at which the water flows is proportional to the square root of the depth of the water remaining in the tank. Initially, the tank is full to a depth of 4 meters. After 15 minutes, the water is 1 meter deep. How long will it take for the tank to empty? So here's a diagram that shows the condition of this water tank at, when h meters of water is left as the height in the tank, okay? What is the first thing that we can do in this question? Well, it looks like we're given time and height information about water flowing out from this tank. We also know that this is a cylindrical tank. Okay, so that means the rate at which the water flows is proportional to the square root of the depth of the water can help us to relate volume, the rate of change in volume, to the proportion of the square root of the height of the water inside. Okay. Next, we notice that we have a volume V, time T, height H, 3 variables here. It doesn't seem reasonable to be dealing with all 3 variables at the same time in one single equation, which means that there must be a way for me to change one of them or rewrite one of these variables in terms of the other. Because the information we are given, 15 minutes, 1 meter deep, we know that we're going to keep time and height, which means that we have to look at how we can change dV by dt as a rate of change in height instead, okay? So on the side, since we know volume of a cylinder is pi r square h, then we can say that V is equal, or V over pi r square must equal to h. We also know that the radius of the tank is 1 meter. Okay, so we can say sub r equals to 1, which gives us h equals to V over pi, which also implies that the rate of change of volume, dt, is equal to pi times the rate of change of height. Okay. I'm going to label this relation to the original differential equation 1. Now I'm going to sub 2 into 1. Which gives me pi dH over dt equals k square root of h. We have a differential equation where we can separate the variables. So now I'm going to keep all the h's on the left, which means that the square root of h now becomes h to the power of negative 1 over 2 dh. And on the right side, I can have 1 over pi and then k like that. Okay, let's integrate. On the left side, I have h to the power of 1 plus negative 1/2 is 1/2 multiplied by 2 because it's divided by half. And then on the right, k is constant, so k over pi t plus c. We could isolate for h here, but we can also use this relation to do the substitution. So now we have when t is 0, the original depth or height of the water is 4. If I plug it in, I have 2 square root of 4 equals to c, which means that c is 4. That gives me 2 square root h equals to k over pi t plus 4 as an intermediate equation. Then we also know that after 15 minutes, I remember, so when t is equal to 15, the height of the water was 1 meter. So plugging this in, I have 2 times square root of 1 equals to k over pi times 15 plus 4, which gives me 2 minus 4, negative 2. Pi over 15 equals to k. Okay, so putting this all together, we now have 2 square root h equals k is negative 2 pi over 15, but this is over pi, so times 1 over pi t plus c, which is 4. So the pi's will cancel out, and I have 2 square root h equals negative 215 t plus 4. Divide everything by 2 and square. So I have negative 1 over 15 t plus 2 squared. Okay, so that's the relationship we have. And now we're interested in finding when will the tank empty. So the tank empties when the height is equal to 0. So 0 equals negative t over 15 plus 2. Okay, so the square, it doesn't really matter. I have 1 over 15, t equals to 2, t is 30. Okay, so the tank empties after 30 minutes. Okay, so now let us turn to a very common application of differential equations, which is to model population growth. As we know, you have probably heard that population growth follows an exponential model, but a lot of times exponential models would ignore the fact that there are many external factors that can affect the carrying capacity, which is like the maximum population that a certain community or environment can really sustain life. And also population can be affected by limited resources such as food supply, natural catastrophes, diseases, and war. So a more realistic model for most population growth is known as a logistic growth. In a logistic growth, as you can see on the graph here, it begins by following an exponential model, but eventually, because of these external factors, the population growth will taper off, will slow low, and then usually approaches like a maximum level, so to speak. Okay, so that's what a logistic growth would look like. And the standard logistic equation can be seen in the box here, can be described as a rate of change in the number of people or the count of a species, so to speak, as k, which is the relative growth, times n multiplied by a minus n. Okay, so this is kind of like the model for that. So here below in example 3, let's take a look. The population of an island is currently 320. Its expected growth rate is modeled by dp by dt in this equation, where t is in years. So we're going to write p as a function of t. So notice how 320 is the current population. So we do have an initial condition value as 0 and 320. Okay, and t is time, obviously. So we can start by writing out dp by dt, which is 0.005 p times 400 minus p. Let's solve this differential equation by separating variables. I have dp, so I'll put p and 400 minus p on the left. And then here I have the integral of 0.005 dt. So the left side here we have a reciprocal of a quadratic. So we can use partial fraction to solve this equation. So here I'm going to rewrite 1 over p times 400 minus p using a over p plus b over 400 minus p. So now I have to find A and B. So if I know that this implies that A times 400 minus P plus BP must equal to 1. If I let P to be 0, then I have A equals to 400. 400A is equal to 1. So A is equal to 1 over 400. And then if I let P to be 400, so I can zero that A term, I have 1 equals to 400B, which gives B equals to 1 over 400 as well. So it's kind of like a common factor on the left side here, which kind of is nice because then this way we can say that 1 over 400 integral of 1 over P plus 1 over 400 minus P dP is on the left side, and then the right side is now 0.005 integral dt. Okay, so I know that I can multiply 400 to the right side, and when I integrate that, I have ln of P minus ln of 400 minus P, right? Because it's a negative P, so I have a negative sign in front of ln. And then the right side of the equation after I multiply 400 is going to be 2t plus constant C. I can write the ln as a single ln, so ln P over 400 minus P here is equal to 2t plus C. Okay, which means that I can do one more step, I guess. P over 400 minus P is now e to the power of 2t plus C, but then e to the C, I can write it as a constant A. So that's good. This is like a general solution. So from here, because I do have the initial value of 0 and 320, I can substitute that to find the constant C, which gives me a particular solution. So let's see, what do I have? 300 is P, right? So 320 is P over 400 minus 320 equals to A times e to the 0, which is really 1. So A is what? 320 over 80. So zeros cancel. 32 divided by 8. That's 4. That means I have now P equals to 4 e to the power of 2t multiplied by 400 minus P. So I'm going to gather all the terms with P in it by first expanding the right side. So P is equal to 1600 e to the power of 2t minus 4e to the 2t P. So if I bring that term to the other side, I get a plus 4e to the power of 2t times P. Factoring P, I have the following. Over 1 plus 4e to the power of 2t. And this is the model for the population growth of the actual population after t years on this island. Okay, so now using this form or equation, B, find the population after 5 years. So that means I'm looking for P of 5. It's 1600 e to the power of 2t, so now it's to the power of 10. 1 plus 4e to the power of 10. And this works out to 400. It's like 399.99999, something like that. Okay. And then part C. Find the time taken for the population to reach 350. Okay, so let's substitute 350 into the function. I have 1600 e to the 2t over 1 plus 4 e to the 2t. So cross multiplying, this gives me 350 times 1 plus 350 times 4. So times 2 is 700, so 1400 e 2t. This is 1600 e to the power of 2t. So gathering the e to the power of 2t terms, I have 200 e to the power of 2t equals to 350, which means that I have ln of 350 over 200 is 7 over 4. Okay, equals to 2t. So using a calculator, you can do that. Calculation t is 0.279 ... So this is in years, but this is not a good way to communicate, to people. So let's convert this into something that can be easily understood, like how many months this is, right? So times this number by 12, you get 3.36. So this is really 3 1/3 of a month. So like 3 months and 10 days. Right, or 3 months and 10 or 11 days, something like that. Okay. All right. So part D. What is the limiting population size? So here, when we talk about the limiting population size, we're really, try to extrapolate this model to, further right when time gets close to infinity. So essentially, we're thinking about limit as time approaches infinity of 1600 e to the 2t. So kind of like how you find a horizontal asymptote, if that exists. And we know this is a logistical growth, so we should have a limit. So let's imagine this. Right now, if I look at e to the power of 2t, it doesn't converge, right? Because it's a growth, and then at the bottom is the same thing. But what if I divide every single term by that? So if I divide 1600 e to the 2t by e to the 2t, I get 1600. And then 1 is now e to the 2t at the bottom, and then here plus 4, something like that, right? So now, if t gets really big, e to the power of 2t gets really big, but 1 over a large number is 0, right? So now, we know that the green term approaches 0, not just that denominator, but the whole term. So that means we're really looking at 1600 over 4, which is 400. Okay. And if you graph this with technology, so that's another way to try to picture it, but you kind of have to make your horizontal scale quite far. So this is, t, p to the power of t. So you started from a certain population, and then you're going to notice that the growth is going to taper off eventually at the level. I shouldn't overlap them, so let me make it just slightly higher so that your graph doesn't really cross it. But you'll see that over time, the population will reach or will approach 400. Okay, so let's write down the conclusion. Therefore, the limiting population size is 400. All right.